My name is Emma Power. I'm from Conception Bay South, Newfoundland, and I graduated from Memorial University from mechanical engineering a couple of years ago. So I decided to do engineering, firstly because I ruled out medicine. So when I was younger, I thought I wanted to do medicine. Then I realized it was a lot more one-to-one with people than I'm suited for. So I'm more of an introvert. I always liked science and math. So that's why I was leaning towards something like that, something in sciences. But I realized that medicine didn't really suit my personality so well. So after I pushed that aside, I realized that engineering really was a good match. It still has all the science concepts, or even more science concepts, different types of science. Still had all of that, had a lot of math, which I did like as well. You do have to like it, it's true. But also it had a bit of creativity to it. So engineering is basically about problem solving and using science to solve practical problems or problems that exist in the world. So I liked that, whereas in medicine, there's a certain way you treat a certain illness, and that's kind of, you stick with that. You don't experiment a whole lot with your patients. But in engineering, the whole point is to think about new solutions to problems. And I liked that aspect of it because I do have a creative side as well, which you'll actually see a bit later. So that's why I chose engineering. I also saw engineering as a good path toward working in the climate change space. So I knew since high school that I was really passionate about the environment and trying to, that's my cat scratching his little head and the collar moving. You might see him later. Oh yeah, here he comes. Nope, lying down. Okay. Anyway, I really wanted to make sure that my job was something that I felt was important for the world, something that I was passionate about, and that was largely about trying to make the earth a better place and as comfortable as it can be for us in the future. So while medicine is important and helping people individually is important, engineering can help lots and lots of people at once. So trying to find solutions to some of these huge global problems, in the end will benefit everyone. So that's why I did what I did, and it did work out. The job that I got is, my title is kind of fluid. I do a lot of stuff, but sustainability consultant is how I would usually describe it to someone. So I do anything to do with helping a client, which could be a person, a business, a town, whoever, another company, helping them to lower the environmental impact of whatever they're doing. So if they are building a building, we'll try to tell them how best to build that building so that it produces, the least amount of emissions. We'll get into greenhouse gas emissions soon. Uses the least amount of energy that it can, is efficient in its water use and waste production and everything. Waste is a big one actually. So for larger clients like a town, we help them decide how can they manage the waste from all the residents. So that's applicable to the household level too. How can we produce less waste? How can we turn our waste into something useful again instead of just throwing it out? So those types of things to help reduce the human impact on the planet. So we'll get into more of those things now, I suppose, while I've transferred over from my intro. So some of the things that I do as a sustainability consultant or a climate change consultant or whatever you want to call me, one of the main things is greenhouse gas emissions calculations. So you've probably heard a bit about what climate change actually is. What causes it is what are called greenhouse gases, or gases in the atmosphere that trap heat. So because we many years ago started to burn oil and gas, we didn't quite have a good idea at the time what it was going to mean. We knew quite a while ago, but we decided to start burning all of these gases, and what they have ended up doing is trapping more heat on the earth than we'd like there to be trapped here. So the physics of all of that, you might have seen in a textbook, or you could look it up later. I won't get into that. But right now, our main challenge is to stop putting more gases up there because we cannot afford to. There's too much in there already, and we're actually probably going to have to try to suck some of it out somehow. So that's a whole other challenge. So right now I'm not working in trying to suck them out. That's another technology kind of person, but we're trying to reduce what we're putting out there. So we call that climate change mitigation. Mitigation meaning to prevent sort of or reduce potential impacts of just trying to make it as least bad as we can. So a lot of what I do is looking at different processes or different activities that we do in our day-to-day lives and how they produce emissions and how we can reduce the number of emissions that are produced overall. So to do that requires a bunch of math, but also a lot of analysis of previous scientists' work. So we'll get into the activity and you'll explain better, but a lot of what I do is reviewing the research that has been done about what emissions result from what and what those numbers actually are, and if they're applicable to things that are happening in Newfoundland or if they're different from something happening in Ontario, because sometimes that's the case too. It depends on a lot of things. So for a particular client, a business or a town or a person or whatever, I'll take the data of whatever it is they want to analyze. So maybe it's a house. So I'll need to know all the energy they use, whether that's electric or from different fuel types. So maybe they have like an oil furnace in their house. I'll need to know that, the gas you burn when you drive a vehicle, and even the waste that is produced from a house, for example, causes emissions too. And that happens in the landfill. So landfill emissions are a whole other thing too. But basically that's what I do. I take all that information, I look at the science that was done before and what numbers make sense to use to calculate the impact of that person's set of circumstances. And you're going to try to do that with my activity. So along with that, some of the other things that our company does, I didn't even say what it is. The company is called Fundamental Inc. So Fundamental Inc. also does renewable energy. So we can help to install solar panels, wind turbines, those fun things. And that is a fun part of my job. So I'll help to size those. So if I know how much energy a building will need, we can figure out how many solar panels will be required for that. We also do work with, and I've mentioned it a little bit, waste reduction. So I've done a lot of emissions calculations to show the difference between putting waste in a landfill or composting it, or the organic waste anyway, like the kitchen scraps and food and all those organic things that were once alive that we've used and are now ready to dispose of. If you compost that, the emissions are way less than if you threw that in a landfill. And there's science behind that too. I don't want to overload you with information, but there's a difference in the emissions from each of those things. So I spent time figuring that out, and then we use those numbers to show people, this is why you should compost. Here are the numbers, it's a fact, this is why. So I did a lot of that. Recently I started to learn how to do building energy modeling, and what that means, it's very similar to kind of what I talked about, making a home or any kind of building as energy efficient as we can. You can model that in computer software. So a building doesn't have to exist yet. It could be just an idea before you're going to build it. But we can kind of draw it up, sort of like if you're going to draw a house in, I know sometimes in games you can, I used to play The Sims, that's probably not even cool anymore. But when I played The Sims, you could build a house. So it's sort of like that. You build the house, but then you tell the program how much energy things are expected to use and how much insulation's in the walls and those kinds of things, and it'll tell you what they expect the energy use overall to be throughout a year. So I'm just learning that. I can't say I really do that well quite yet, but that's basically what I do, most of the things. Lots of other things thrown in there. It's a small company. It's just me, 2 employees, and then the founder of the company, 2 other employees other than me. So just the 4 of us, and it's quite fun. We all work remotely. So I am currently where I work, which is my house, and I quite enjoy that. I work whenever I want, really, as long as I get what I need to get done. It doesn't matter when I do it, and that really works for me. I've always been a very independent worker. I can manage myself pretty well, and I could always keep on my own study schedule and everything like that. I was I'm pretty self-motivated, so that works for me. And of course, we do communicate with each other all the time. Me and my coworkers, which are all awesome, basically my friends. So I really enjoy it. My current only in-office coworker is my cat. Maybe I'll throw up a picture of him or something in here. He's not coming over at the moment. But yeah, so that's my day-to-day life is a lot of computer stuff, basically entirely computer stuff. We have a lot of conference calls for our meetings, or just regular phone calls. And I'm in Excel a lot. Excel, the spreadsheet software for math. But I also do some technical writing, documents. And then another cool thing that I do, and I was going to talk about it at the end, but maybe I'll just do it now. I happen to have some other experience in graphic design. So graphic design is totally different from engineering or sustainability consulting or anything. It just happens to be something else that I learned. I actually learned it in junior high and high school, and I competed in Skills Canada competitions. So Skills Canada, Newfoundland and Labrador is another organization you may have heard of. And I competed in graphic design for 5 years or so. So I learned a lot doing that, and I use my skills a lot now. So I'm going to throw up some pictures of things that I've done in my video later. But I use those skills way more than I even thought originally. I use them not every day, but like very often. So I guess the first thing to note is I made the company's logo, so that's kind of cool. I have my business card here, which I made, so it's going to be backwards. I just realized that. Darn. I'll put up the real files. But yeah, so I made the company business cards, our resumes, those basic things. But I've also made some diagrams for different projects to help because a lot of the times it helps to illustrate something in a visual way to a client or anyone really who's going to look at the content. So I make a lot of diagrams to go along with either proposals or project presentations, things like that. So given all of that information, I'll talk about my activity now. As I mentioned, the activity is about doing your own greenhouse gas inventory, or at least practicing one. So for activity 1, I've given all the basic information that you need. So it is a math exercise, but it's not hard math. It's only multiplication and whatever else you might need to do to convert units and things like that. But there's one basic formula. So no calculus, nothing weird. So there's one formula that is the basis of how emissions are calculated. It is that simple, really. What the tricky part has to do with some of the numbers that go in the formula. So you don't have to worry about that because I've given you all the numbers. But those numbers are a large part of what my job is. So figuring out what those numbers are, if they're appropriate for the location, and the energy sources that are involved, and making sure that they're up to date because the science is updated a lot. So we're still trying to figure a lot of stuff out, and so I have to annually revisit the new documents that are released and find out if my numbers are changing or my formulas are changing. But this is the basic formula. So every other emissions formula is some version of this. It might get more complicated, but it comes down to this. So we have activity data, which is just the word we use for the thing that we're doing and how much of it we're doing. So in the table here, I break that down into using electricity, using fuel, like gas in your car, and producing waste. There are more things that you can do that have emissions impacts, but these are what we're going to talk about here. And then how much you do, however we measure that, is the data that goes in the formula. So I've written that out clearly here as well. So for your electricity, that comes through your house as kilowatt hours. And that's just a unit of energy. You don't need to worry about where that comes from. But you might have heard that word before. So the electricity cost, for example, is given as a number of cents per kilowatt hour. So that's what you need there. For fuel, you use liters, same as a liter of milk or whatever, however much you're pouring into your tank. And then for waste or garbage, we're talking about kilograms, so how much it weighs if you were to weigh it. So that's activity data and the unit associated with your activity data. And what's important is that your unit of that data matches the unit that is in your emissions factor. So the emissions factor is the big part of this formula that's going to give you your answer for how many greenhouse gas emissions are produced. And it's the emissions factor that other people have to figure out. So they have to do experiments and all kinds of math and chemistry to figure out, when you say burn this much gas, how many greenhouse gases, or like, because there's a lot of gases produced, but the ones that cause global warming are the ones that are contributing to climate change. How many of those are there? So somebody else has done that for gas, for example, and that's the number that we use to multiply by the amount that we're burning to figure out overall what has happened. So what did you just put into the air when you drove from here to Walmart? What just happened? So that's what those numbers mean, and you'll see the units on that. You'll see the unit we talked about on under the slash. So kilowatt hours or liters of gas or waste. But the TCO2e means tons of carbon dioxide equivalent, and that's a mouthful. And you don't really need to know exactly what that means. But basically, there's more than one greenhouse gas. So we often hear about carbon dioxide, and that's an important one. But there are other ones. There's methane, there's nitrous oxide, there's certain types of refrigerants, which are to do with like refrigerators or heat pumps and air conditioning and stuff. But all of those don't act exactly the same in the environment, in the atmosphere. So to make it easier, scientists decided, let's just have one unit, and we're going to convert them all into this one unit. So it would kind of be the same as if suddenly the world was like, you know what, we don't need Canadian dollars and American dollars and euros and all these types of money. Let's just convert them all into one amount of money. That's sort of what's happening. So they've decided to convert everything into this one unit, and that's called tons of CO2 equivalent. So it's compared to carbon dioxide because that's the main one that everyone knows about. But it's considering the impact of the other ones compared to the impact of carbon dioxide. So it's a bit complicated to explain. I won't go into it further, but just know that it's considering all of the gases, and this is the unit that was decided was good to use. So we'll stick with that. So those are the numbers we need. The activity data, how much of the thing that you're doing in the units that I've laid out here, and then you're going to multiply that number by the emissions factor for that particular activity. So there's a different number for each thing, because 1 kilowatt of electricity is not the same as 1 liter of gas. Not the same at all. So that's why we have these different numbers. So that's the basic explanation of what the math is. And that's really all you need. So I have some extra words there you can read through if you want to. You don't have to. But then the actual questions, I'll leave to you to read through. So there's two parts. The first one is kind of the original situation. So I've made this hypothetical situation. Her name is Emma, just because I picked it to be easy. But she's living in a house with a certain number of people, and they use so much energy every day, every year, and they drive a certain amount in certain vehicles, and they produce a certain amount of waste. So that's all included there, and I want you to calculate the carbon footprint. So that's another word I probably should have mentioned earlier. Carbon footprint is probably a word you hear more often than a greenhouse gas inventory, but they're the same thing. So I probably could have clarified earlier, it didn't come to me. But basically carbon footprinting is what I do, all the same. So that's what you're going to do. You're going to calculate the carbon footprint of Emma's household in 2019. So usually when we do an inventory, we talk about a particular period of time, usually a year. So that's what I'm doing here. 2019 is part A. Then there's a part B, which I know everyone hates when that actually happens in your homework, but there's a reason for it. So in part B, some things have changed. So they've decided to make some changes at home. And you're going to find out if that made a difference to their carbon footprint. And so it's basically doing the same thing again. You do the same thing again with slight changes, and I want you to compare the results at the end. So compare part A and part B and see what happened. one thing I wanted to highlight in this video is that everything that I've proposed between part A and part B, so the changes that happen, are very reasonable to do. Anyone could actually do them. And the result that you see is accurate. So the emissions factors I've given you are right, and the reductions that I've written about are pretty reasonable. So I wanted to make sure that that was the case with whatever I gave you. It's not like this is a crazy, unrealistic example. It really is a realistic example. So I hope that helps. So that's activity 1, and you don't need to gather any information. You can just use what's on this sheet, and you should be good to go. For activity 2, I wanted to include something like this in case you really wanted to find out, and if you had the time, and if you really wanted to dive in, you could do this for your own house. You just need to get the information yourself. So whereas in activity 1 I said Emma does this and her family does this and here are all the numbers, you can get those numbers for your own house if you want to. So I have a few steps here, but it's basically the same thing as before. But I have a space here for you to find your own electricity data. So you'll probably have to ask your parents or whoever to find this for you. You usually can find it online in your Newfoundland Power or Newfoundland Hydro account, but you can find the data for that. And then this time there's different emission factors for different places. And that's because the electricity is not the same everywhere in the province. It comes from different places. So the number that you see here has to do with where the energy comes from, how it's generated. So you might be thinking, well, why is it 0 in Central and Western Labrador? And that's because it's 100% hydroelectricity. So that's considered 0 emission. Whether that's totally true is another conversation altogether, because there's still probably some things happening. But overall, it's just water turning a turbine, and nothing is burned, no gases are burned. So we call that 0. Whereas for the rest of Newfoundland, or for the island of Newfoundland, we still have a fuel being burned at a thermal generating plant. So that's causing some emissions. And then in northern and southern Labrador, most of them are on diesel generating systems, diesel being the same kind of diesel you use in a truck or whatever, but they're burning fuels in those places too. So that's why the emissions factors are so different. And I wanted to have them all there because it does matter. So I won't explain too much of the rest of it because I don't want this video to be crazy long, but I have another section here for building fuel use in case you burn oil for your heat or something. And then transportation and waste are the same as activity 1, basically. It's just a matter of calculating it for yourself. And for waste, I didn't mention this for activity 1 yet, but it's hard to estimate how much waste someone actually generates. Most people don't measure it, but there have been studies done and research done. So what we're going to use is 330 kilograms per person as the estimate. And if you think about that, that's a decent amount. Like, if you were to see it all right up front, 330 kilograms of waste, it's a lot. So maybe that number alone can help you reduce your waste. Okay, I'll stop now. This is getting a bit long. I could go on and on about most of these things for a long time, but I won't. I hope you enjoyed it. I hope you have learned something, and maybe you will consider a job in climate change mitigation. We need you.